Hello everyone. Oh my gosh, it's been so long since my last video. I decided to compete in the Div 4 round today, and yeah, I did pretty well. In contest, I actually solved from A to E, but afterwards I was able to upsolve F, and then so I'll be explaining the problems from A all the way to F. And yeah, so you know what? I realized I'm pretty sure most, if not all, of these question titles is like a Taylor Swift song. So that's interesting. I realized when I got to like problem C. Okay, so first, problem A. We're given a string S with exactly 10 lowercase letters. Okay, and then we want to compare it to the string Codeforces, which is also of length 10. And then our goal is to see how many like indices where our given string differs from from the string Codeforces. Okay, so if we have um, string Codeforces and the given string S, so let's say S is equal to all A's. So remember, S can only be exactly 10 in length. So this is like A, all the way of length 10. We want to see how many positions where the letters of Codeforces differ from the given string. So that would be different. So that would be 1, next is 2, 3. But if instead of A's, we had like C, O, and then let's say an A, F, F, O, and so on. C is not different from C, so this we wouldn't add 1 to the answer. O is not different. D is different from an A, so the answer is 1 right now. E is not different. E is different from F, so we add another 1, so that makes our answer 2. And then we just do that whole thing. Yeah. So the code is going to look something like this. So I set the like string answer to Codeforces, and then I input the string S, and then for each index from 0 all the way to 10, I check whether S is different from from answer. And if the strings at that index I differ, then I just add 1 to the count answer, and then at the end I output the number of indices where answer differs from string. Okay, easy problem. All right, next problem. Blank space. Okay, so we're given a binary array A of n elements. And so a binary array is an array consisting of only zeros and ones, okay? And then we want to find the longest consecutive elements consisting of zeros, okay? So let me delete this real quick. So if we have 1 0 0 1 0 0 0 1 1 1, blank space is a 0, like consecutive zeros. So let's just put 1 0 at the end. Okay, so incrementally, which means like going this way, we see that the first element of the array is a 0, right? So now our largest sequence is a 0. Is 1, because this is of length 1. But now we have a 1 blocking it, so we have to like terminate this search. So the largest answer is still 1, but then we can't add 1 more to it. So now the next longest sequence of zeros is over here, which is 2. So now the new answer is 2. But then over here, we have a segment where it's all zeros, and that is of length 3. So we can take away this 2 and then add a 3. So now the answer is 3. Okay, so how do we do this? Well, we have to simply iterate over all the characters of the string A, or of the array A, because technically it's an array. And then we keep track of the current number of zeros, current consecutive number of zeros. So in this case, if we take all this away, in this case right now it's 1, but then as soon as we get to a 1, like over here, this 1, we can save like the previous largest and store that into a variable called answer. So let's say answer right now is equal to 1. Next we go to, okay, so now we iterate to like the third element, which is this 0, and then our current is equal to 1. We iterate again, we find another 0, so now we add another 1 to the current count, so that'll equal to 2. And then when we reach another 1, we have to terminate this search. So current is turned into a 0, and the answer becomes a 2 because 2 is the next largest. Okay. And then we do the same thing for the 3, and then we end up getting 3 for the answer. So now here's the code. Again, pretty simple. We just input the elements of A, and then for each index from 0 all the way to n, we find if a sub I is equal to 0, then we add 1 to the count, because we're keeping, so count is the variable that keeps track of the current length of zeros, the current blank space, okay? But then once we reach a 1, we have to terminate the search, so we set count to 0 because there's no more consecutive zeros, but instead we keep the answer in a variable called max. And then maximum keeps the largest sequence of zeros. So in this case, it would be 3. Or in the case I like drew out earlier, it would be 3 because count is first 1, then it's 2, then it's 3, and the largest is 3. Okay, moving on to question C, Mr. Perfectly Fine. So Victor wants to acquire skills, and he reads book I in m sub I minutes, and then he wants to find out the minimum amount of time that it takes to acquire both skills. So what a skill is, as you can see over here, so we're given this column, so this column, the 2, 3, 4, 4 column, is going to be the number of minutes it takes to read the book. And then the right column, 0, 0, 1, 0, 0, 1, is going to be like the contents of the book, okay? And in the problem statement, it explains that in order to become Mr. Perfectly Fine, first let me delete this. Okay, so you're given m as the number of minutes, or m sub I as the number of minutes that it takes to read the book I. So book I, you're given m sub I minutes, and you're also given a string of length 2. So that you're going to be given 2 digits. So this is first digit, this is second digit, and this could either be 0, 0, 0, 1, 1, 0, 1, 1. So one of these options. And then your goal is to find out the minimum amount of time total it takes to read both books. So read or grab both contents of the books. So to do so, we have to get ones on each side. So there has to be a 1 in this. Sorry, let me delete this real quick. There has to be a 1 here and a 1 here. But that's not the only case, okay? So if you have another index where, let's say, m sub j, and then you're given a 1 and a 0, obviously this doesn't meet the case because this 0 is not sufficient in the requirements in order to produce the answer. Oh, and also, by the way, if we find the answer, we just output the minimum number of minutes, right? Okay. And if not, we just output -1. Okay, so in this case alone, if we only have one possibility, this won't be sufficient enough because this works, so the first content works. So I'll call um, I'll call the first like content, so this part, this number, I'll call that A, and I'll call this B. The second one, I'll call it B. Okay, so in this case, where we have 1 and 0, A is going to work, but B isn't, right? But then we need 2 ones, so it needs to be a 1 and 1. But if we have another M sub I, where it's like this, content A is 0 and content B is 1, then he can read both books and then still get information from here and here, therefore making the answer yes. Okay, so how do we solve this? So there are only 2 cases we need to look for. Actually, no, 3. Okay, the first case is if it's not possible. And the answer is not possible if there are never 2 ones. Okay, so if we have a 0 and a 0 as a first string, a 0, 1 as a second string, this isn't possible because there's only going to be a 1 in this index, right? There ends up only being 1 out of all these indices. Out of both indices, technically. They're only going to have a 1 over here, but in this case it's going to be a 0, so this will not work because it needs to be a 1 and 1, remember? Okay, second case is if we have an element where, or we have an index where there's a 1 and a 1, then the minimum answer would just be M sub I. So if there's a 1 and 1, then we don't need another 1 and 1 to make it work. All we need is just this. All Victor needs to read is just M sub I, and then he'll be able to become Mr. Perfectly Fine, right? But the third case is going to be 1 and 0, let's say 0 and 1. Then this ends up being okay, because, so let's say this is M sub I, and this is M sub j. Well, this ends up being okay because there's a 1 in the first row, or first column, sorry. And then in the second column, there's also a 1. So this checks out, okay? And then so in this case, the answer would just be the sum of M sub I and M sub j, because you need both of these books. You need time to read both of these books. So it ends up being, so the total number of minutes he spends reading is going to be the sum of both of these. Okay, so how do we put this into code, right? Well, actually, let me back up. Okay, so in the first case where it's not even possible to read any amount of books to make it work, we're given only like zeros in the columns, right? Or there's never going to be 2 ones. So if we identify that, then the answer is always going to be -1. So let's say, in this case, we can keep track of the number of ones in column 1. So this is column 1, this is column 2. In column 1, there's going to be a 1, of course, because there's at least 1 in column 1. But in column 2, there are no ones at all, which means that we have to add a 0 here, making this impossible. So to keep track of the ones and zeros, and then if there are at least 1 in both columns 1 and 2, then the answer will be available. Otherwise, it won't. Okay. So let me just go over the code, because I think it's going to be easier once you see the code to finally like grasp the answer. I think there are easier ways to do this, but okay. So I kept 3 variables, answer 1, answer 2, answer 3, and I set them to the largest integer limit. And you can do this using the keyword int max. And then it's going to be around like 2 billion. Okay, so then I insert A and B. A is going to be, oh, sorry. So A is going to be the minutes in this case. So it's going to be M sub I. And then B is going to be the string. It's like the string S. So this is A, this is B. Okay. And then so if B is equal to the string 1, 1, then I set the minimum of the minutes because 1, 1 means we already found it. He only needs to read that one book, right? So if it's this case where he has 1, 1 and then M sub I minutes, well, in order to become Mr. Perfectly Fine, he has to have 2 1s. And this fits the description perfectly. So all the answer is just going to be M sub I. Okay? And you want to find the minimum of that, because always like trying to minimize the amount of time he reads, right? So the second case is if there's a 0, 1, then you just find like the minimum amount of time it takes to read that book. And then if it's a 1, 0, then the minimum amount of time to read that book, okay? So over here, if answer of 1 is equal to int max, which means that there is no case where B is equal to 1, 1. So the reason why this whole logic works is that initially, remember, we set answer, kind of messing this up. Okay. We set answer of 1 to the largest integer limit. And then if by the end of like all the minimizing elements and stuff, it's still the largest integer limit, then we know that we have never even like inputted a 1, 1. Okay? So we can get rid of that possibility. And so the keyword and, which means that both statement 1 and statement true have to be like the value of 1, like true, in order to work. Answer 2 is equal to int max, which means that we have never even seen a 0, 1, or we haven't seen a 1, 0. So, okay, so say we're given 1, 0 and 0, 1. If we have never seen a 1, 0, that means we can never even make a 1, 1 possibility. Because without a 1, 0, then a 1, 1 possibility isn't even true, right? So we can have 0, 0, 1, 0, 1, 0, another 1, 0. Okay, so this code, all it's saying is, in this part, it's like if answer 2 is equal to int max, meaning we have never encountered a string where the answer is, where the string is 0, 1, then we can just output false, because we can't even make a string of 1 and 1 if we don't have 0, 1. With the 0, 1, we can have a 1, 1 string, because we have a 1 here, perfect. But if we don't have this, we can't make it. So therefore, answer is -1. Okay. Next case is if answer 1, which is the 1, 1 case, is less than answer of 2 plus answer 3. And this works because we have two options to form the answer, right? Let me delete this real quick. Our two options are either using, I'll keep that. All right, is either using a 1, 1 string or a 0, 1, 1, 0 string. In this case, all we have to do is take, in the 1, 1 case, all we have to do is take M sub I as the answer. But in this case, we'll have to take M sub I plus M sub J. Okay. Oh, wait. Like that. Because we'll have to add the minutes of reading this book plus the minutes of reading the 1, 0 book. Right? So we have to find out the minimum of reading just like the 1, 1 book and also reading both books. Okay, moving on to problem D. Gold Rush. This is a cool problem. So we're given two integers. Sorry, let me delete this real quick. Okay, we're given two integers, n and m, and then our goal is to break down n so that m is like, oh sorry, let me rephrase that. Okay, so n is the starting pile, right? The starting size of the amount of gold. Is it gold? Yeah, it's gold. And then our goal is to break n down so then we have a pile with m gold. Okay, so if we have 6 as n, so n is equal to 6 and m is equal to 4, well, to break it down, we break it down into a size k and then also a size 2k. So it has to like split into exactly k and 2k, right? So if we take n splits into k and also 2k, well then the sum of these is going to be 3k. So essentially n breaks down into 3k, right? So n must be divisible by 3, first of all, because then this all like works with integers and not decimals, right? So n must be divisible by 3, right? Okay, so in the case where n is equal to 6, 6 breaks into 3 of 2's, okay? And then we want to have 1, 2. So you know how we have a k and a 2k? Well, if we move it over here, k is equal to 2 and 2k is equal to 4. M is equal to 4 and we have a pile with 4 in it, so the answer is yes. I guess I'll just leave it here so it's easier to like understand. Yeah, so we have to output yes if it's possible to get a pile with breaking it down, and otherwise no. And then notice we don't just break it down once. We don't just break down n once. So if we have n is equal to, let's say, 18 in this case, and m is equal to 4 again, we can break 18 down, or let's just write the value. 18 breaks down into k and 2k, so therefore it breaks down into 3k. So 18 divided by 3 is equal to 6, meaning that we have 3 of 6. Okay, and now k is equal to 6, 2k is equal to 12. Alright, so these are our new gold piles. So 6 and 12 is our new pile of gold. Alright, well, both of these are divisible by 3, so we can do the operations on them. I'll make it quicker this time. So we have 2 and 4 for 6. So this is 6. And then also 4 and 8. Oh, well, what do you know? We have a 4 here. So now this works. M for 4 works because we have a 4 in one of the gold piles. Okay, so this looks a lot like a recursive function where we can keep like plugging in the value again and again and breaking it down and then finding whether any of the elements ever is equal to m. We don't have to break it down all the way to its core. We just have to have a value at some point in time where it's equal to m. Okay, so what the recursive function would look like is we take n, so n is equal to 18, we break it down into 3 parts, so 6, 6, and 6, because it's divisible by 3. So first we have to make sure it's divisible by 3, n is divisible by 3. Okay. Once we break it down, we have to like reformulate the piles of gold. So in this case, this would be by itself. Sorry, this will be by itself, and these two will be by itself. Will be combined together. So we have 6 and 12 now as a new pile of gold, as you saw earlier here. Okay, so now we plug 6 as our new n, and then we move it like over here as if it takes a spot. And same with 12 if it's divisible by 3. So we constantly check its divisibility by 3, and then if 3 divides the current n, then we could break it down, and if not, we just like stop there and we return the function. Okay, so I'll show you the code. Hopefully it'll make a lot more sense. super simple code. We just input n and m, and I plug it into the function solve. And so what solve does is, if we visited a certain number x before, we can return the search, right? Because let's say we have, in this case, so all that returning, it's not necessary, but it just saves a lot of time. So if I didn't include the returning, if I visited before, then I can like go through lots of recursive operations, which is not good because it'll waste a lot of time, and then time is like essential for competitive programming. Okay, so let's say yeah, in this case we have 2 4s, right? Well, I guess 4 is not a good example. Let's say we have 36, right? 36 breaks into 12, 12, 12, 12 and 24. 24 breaks into 4, 8. 24 breaks into 8. Wait, sorry, 6, 8 and 3. Oh, no, yeah, 16 and 8. 16 and 8. Yeah, so this is our new gold pile. None of these are divisible by 3. But anyway, so let's pretend that 8 is divisible by 3, or this number is divisible by 3, and this number is divisible by 3. If we keep going, then we're just wasting operations. If we keep breaking it down and breaking it down and breaking it down and breaking it down, then we only need to do it for one of these. So if we did it for this 8 over here, we don't have to do it for this 8 because we're just wasting operations. We already know all the gold piles of this 8, so this is essentially useless, right? Okay, so now we know what that visited array is for, and I made it a map just like so I can fit more integers. And then so I set it to 1, meaning we have visited this x, and if x is divisible by 3, because remember we have to break it down into 3 parts, k and 2k, then I can re-plug in x over 3 as the new x, and x over 3 times 2 as the new x. Remember, because in this case where x is equal to 18, let me delete the 36 because it's confusing. Alright, if we have 18, break it down into 3 parts, 6, 6, 6, and then we plug in this 6 back into the function, remember over here, but then we also have to plug in 2 times 6, which is 12, over here, back into the function. So that's why we do x over 3, which is 6, times 2, which is 12, and then plug that back into the solve function so we can repeat the process again. So this is the recursive function that we use to break it down. Okay, hopefully that makes sense. And then, oh yeah, over here, if we have visited m, so if like m is the size of the gold pile, then it works. Then we could just output yes. Otherwise, no, because we can't break it down. Next problem, the lakes. Yeah, so you're given a grid of n by m elements which are non-negative. So non-negative integers. So that means 0 all the way till over here it says 1000. Okay, so this could be an example of the grid. And then your goal is to find out the sum of all the positive integers that can be like reached from one another without going into a 0 cell. So that sounds confusing, I know. Let me explain it further. In this case, we have 1, 2, 3, 4. Let me delete this real quick. We have 1, 2, 3, 4. This looks bad. Okay, so in this case, this is one volume, so 1, 2, 3, 4, so the sum of that would be 10, because it's 1 plus 2 plus 3 plus 4 is 10. And then over here, it's just 5. So the answer is going to be 10, because that's the largest of 10 and 5. Okay, well, how did I come up with that? How did I jump to that conclusion? Well, because if we start at this 1 at the top left corner, we can reach 2, we can reach 4, We can only reach adjacent elements. So 2, we can reach 4, we can reach 3. But then we can't reach 5 because we can't go diagonal. And then we can't go to 0 integers, right? Because these zeros are like basically barriers. They're basically walls where you can't cross. So if you ever see a 0, you're stuck. You have to go around it. But in the case where we have, let's say a 4 and a 4 and a 4 and a 4 and a 5, or 6, sorry, and a 5 and like a 1, we can just follow this path. So we can take all of these elements. Because if we start at any of these elements, like we could even start on this 6 over here. Sorry, that was a bad arrow. We can start on this 6 over here. We can travel to this 5 next, then this 1 next, then this 5 next, and then moving on to the left side of the 6, we have 4, 4, and so forth. Then we can eventually like grab everything. And then that volume would just be the sum of this whole blob. But if there's ever a 1, or I'm sorry, ever a 0 blocking the path, this 6 over here can't get over to this 1 because there's a 0 blocking it. So this 5 and 1 would be independent of this smaller blob. Okay. So this algorithm is a pretty famous algorithm that we can use called flood fill. And if you know this algorithm, this problem is such a generic flood fill algorithm problem, it's going to be so easy to solve. And essentially what flood fill does is, let me add back this one, delete this. Okay, yeah. So essentially what flood fill does is you can choose an element, and then from that element, the flood fill algorithm will go to all possible directions. So let's say we start on the 4 in the middle. If you choose this 4 as a starting element, then you can travel to this 2 next, travel to this 3 next, travel to this 0 next, travel to this 0 next. And then after traveling to these elements, we'll travel to like the ones around it and so forth. So it's like kind of a spreading type. It's similar to breadth first search, if you know that. But then the thing is, we can't even go to the 0, right? Because these 2 zeros are illegal moves that we can't make. So we have to terminate these zeros, and then it ends up being not allowed. So the allowed moves are 2, 3, and 4. Okay, and then if we keep repeating the process, then it floods to this one, floods to the 1, floods to the 4, floods to the 4, floods to 4, 4, 6. And then once we get to the 6, we can't go anymore. We can't go anywhere anymore because the elements around the 6 are zeros, right? So we have this 0 and this 0, but we can't travel to them because it's not possible because they're zeros, and zeros are an illegal move. And therefore, we terminate the search, and the answer is just the sum of the flooded elements, like this. Okay. Because we see that the rest of the elements here are all zeros, blocking it. And then we can also do this again on the 5 over here. And we end up getting 6 over here. And then whatever the sum is, which I'm sure is larger than 6. And then we find the largest volume. Okay, well, how do we do this? Let me just show you the code so it's easier, and I'll run you through the code. Okay, first, if this confuses you, I'm just setting the visited array I have later to zeros so we can like continue using it. And so I input all the elements, I input the grid, I create a variable answer, set it to 0, and then for each element of the grid, I check if I've visited it or not. Because if I visited one of the elements, then there's no point in going over it again. For example, what I mean is, okay, so initially I flood element 4, right? And then that basically gives us the blob over here. And that's good, right? So in the next search, what I do is I search 1. But 1 will give us the exact same result because it'll basically flood everything over here again, which is not necessary because I already did that search. So that is why I got the TLE, so like time limit exceeded on the first test case. Oh, second test case, sorry. So yeah, there's no point in rechecking any elements in the block, so in the blob. So we only need to do it once, and then we don't need to check. So if we check 4, we don't need to check 1, 2, 4, 3, 4, 4, 4, or 6. We just need to check one of the elements in the blob, and we're fine. So the way I do that is I keep a visited array, and if I visited before at some point in time, then I don't need to check it again, and I move on to the next element in the grid. Okay, so that's what this visited part does, and then continues if I visit it. Otherwise, I check the largest volume by setting answer as a current answer to the largest of like its current value, and also the flood fill of the current element. So flood fill of flood fill of ij just basically gives the coordinates of the element I'm at right now. So in the beginning, it'll be 0, 0, because I is 0, j is 0, which is essentially flooding 4, starting at 4. Okay, so how flood fill works is we use a stack, and I named it frontier, and then we push back R and C into the stack. And then so while the stack still has elements, we take the top off, and then we say that R is equal to 0, C is equal to 0, because it's equal to the top, right? And right now the top only contains 0 and 0. For example, we have the stack, let's just call it F because I don't want to write it down. So right now F contains 0, 0, which is the current elements. All right. After that, we pop it, which means we take the top off, and then we check if it's within the bounds, right? Because if it ever goes out of bounds, so if like it ever goes into one of these areas, I'll just put it -1 as a barrier. If it ever reaches like one of these -1s, or a -1 on the top or to the side or to the bottom, then that's an illegal move, right? So that's essentially what the first if condition is saying. It's saying if it's less than 0, which is illegal, or if it's greater than n, or greater than or equal to n, because we're using 0 indexing, or if the column is less than 0, or if the column is greater than or equal to m, then we know that we have to terminate that search because we're out of bounds, like literally out of the bounds. Okay, but and also if it's equal to 0, so if the grid has a 0 in it, we also know to terminate that search, because remember, zeros are barriers. We can't go to the 0 according to the problem. And also if we visited it before, because if we have the previous flood fill and we've gotten to that element before, then we know we don't have to search it again because it's redundant. There's no point in wasting operations. So all of these conditions, it's kind of hard to keep track of, but you'll remember it. Yeah, you have to just continue and terminate the search if that's the case. Otherwise, to calculate the current volume, we just add 1. We don't add 1. We add the current element to the count of the volume, the current volume. So the current volume adds the elements to keep track of the total size of the volume, right? And then we set that index to 1. And then over here is the final step of of flood fill, and then we just push back the new indices, right? So if we started on 0, 0, we essentially just push back -1, 0, so it goes down 1, so over here, so it goes to over here. We push +1. Wait, sorry, let me restart that. Okay, so let's say this is part of the grid, right? Over here we just add like the new indices, and then I store it into like R change and C change, which is 0, 1, 0, and -1, which keeps track of like which direction it moves now, the new direction. Okay, so in this case we're moving back -1, -1, 0. We're moving to the right to make it 0, 1. So this is independent. This is independent. We're moving down to make it 1, 0. And then we're moving to the left to make it 0, -1. So we add 4 elements into the stack, right? But then two of these elements are illegal, right? So if we go up, oops, what's going on? If we go up, left, oh my gosh, it's bugging. Okay, up, left, down, right, then two of these elements, these two arrows are illegal, so we can't move these. So we essentially take out these, and now the only elements left that work are 1001, and we keep the search going. That's essentially the code, and yeah, a little complicated, but that's it. Alright, moving on to problem F. The annoying one, the so annoying one. Okay, alright, so essentially what this problem is that we're given a graph, and then all we have to do is find out the value x and y. And x is going to be, so we start off with one central vertex, so this will be 15 in this case, because it's in the middle, 15. And we add x new vertices. So if x is equal to 5, then we add 1, 2, 3, 4, 5, connected to the central, which is 15. Okay, and then after that, we add exactly y new vertices to each of these x vertices, right? So for each x, which is like 20, 6, 7, and so forth, we add 1, 2, 3, 1, 2, 3, 1, 2, 3, and you can see they're all like connected to the next one. Okay, so we're given t-test cases n and m, which is the number of vertices in the graph and also the number of edges, okay? And then after that, we're given m like edges, which is between u and v. And then our goal is to find out x and y, okay? So this problem is super easy. There's no like depth first search or breadth first search needed, no graph traversal. It's just like super trivial, okay? So the answer is going to be, so yeah, what we can first do is, like, let's say given the graph, I'll use the starting graph as an example. So we have a central graph. I'll just color it in so you know which one's the center. If we have one vertex, I'll just call them nodes. So one node over here, another node, 4, 5. Because you remember in this sample case, x is equal to 5, y is equal to 3. I'll just put it up there to help you remind you. And then over here we add 3 nodes, 3 nodes, 3 nodes, 3 nodes, and 3 nodes, right? So we can just keep track of the degree. So what a degree of a node is going to be the number of edges that are connected to it. So if we have, if we choose this node over here, where the arrow is pointing to, that node's degree is going to be 4, because there's a node over here, there's an edge over here, an edge connecting here, an edge connecting here, and an edge connecting here. So it has 4 edges connected to that node, right? And so, yeah, so our goal is to first find out how many, like, edges have to be, like, outside, right? So we have to calculate the number of degrees where the degree is equal to 1. So in this case, we're given 1, 2, 3, 4, 5, 6. So it's all going to be the outer layer, right? So in this case, it's over here, plus over here, plus over here. Because as you can see, there's only one edge connecting these two nodes, only one edge connecting these this node, one edge, one edge, one edge. So we want to find out all the one edgers, okay? So it's going to be all the outsiders. And this is the case for all of them because only the outside nodes, so all the nodes on like the very outside of the snowflake is going to be having a degree of exactly 1. Okay, so that's like the one thing to note. So in this case, we'll call that k. So let's say k is equal to the sum of elements or nodes with 1 degree. In this case, it's going to be 15 because there's 3 plus 3 plus 3 plus 3, so that's 15. Let me kind of delete this. Okay, so now we know k is equal to 15. What can we do with this? Okay, well, we know that for each node, there's going to be n minus 1 edges. Okay, so let's think about that. If we have 21 nodes in this case, I'm pretty sure it's 21. Yep, so in this case, it's the sample case. We have 21 nodes. So n is equal to 21. Then we know for sure that m is going to equal to 20. Because for each node, let's say this node, there's exactly one node pointing to another node. For this node, there's exactly one node pointing to this node. The only node that doesn't have an edge pointing to another node, I guess, so pointing to the inside, is going to be the center node. The central node does not point to anything within itself. But I know it's confusing because the center node has 5 edges pointing outside, but I'm talking about pointing inside. So for this node, one node pointing inside. For this node, it sure has 3 nodes to the outside and then 1 on the inside, but it still has 1 on the inside. So if we count the number of nodes, it's going to be 21, while the number of edges is going to be 21 minus 1. So always going to be n and n minus 1 as m. So we can rewrite that as m is going to equal to n minus 1. Alright. This is essential because once we figure out the number of nodes where its degree is exactly 1, in this case it's 15, all we can do now is we can subtract the number of nodes, so that's 21 minus k. So more general form is going to be n minus k, because we subtract the number of nodes on the outside minus the center node. So this is center node. This is total nodes. This is the number of nodes on the outside. Okay, so if we take the total amount of nodes, 21, and then we subtract the number of nodes on the outside, so we remove here, then we're only given this inner length. And then we subtract this center node, so we take that away, we're given the amount of nodes where it's still white. So I'll draw a line through each of them. So 5 is going to be our answer for x, because we take away the center node, we take away the outside nodes, and then all we're given is the answer x, which is the initial amount of nodes we add on to the central node. Okay, so now we know that 21 minus 15 minus the center node is going to equal to 5, which is equal to x, which is our answer. So now we know x, our first answer, is equal to 5. Okay, so now the problem is, how do we calculate y, which is the second answer? Well, all we have to do is we have to take the number of outside nodes, which is 15, and then we have to divide it by x, which is equal to 3, and that is in fact our y. And then how does this work? Well, we know that there are 15 nodes on the outside, right? And then we know that there are 5 nodes on the inside. Well, then to get the number of nodes over here, all we have to do is divide, let me write it at the bottom, outside, oh wait, my English is so bad, outside over the number of nodes connected to the central node, so which is x, is going to equal the remaining nodes. So it's going to equal to 3 over here. It's going to equal to 3, which is our answer for y. Okay, so now we know y is equal to 3. So the code is going to be fairly simple. No graph traversal or anything like that. We just input n and m, u, v, and then d of size n plus 1. And the reason I did n plus 1 is because we're 1 indexing over here instead of 0 indexing. Okay, so I keep track of the count of the degrees. So when we input the nodes that are connected through an edge, u and v, so that means u is connected to v via an edge. And then so we need to add 1 to the count of the degrees of both u and v. Okay, after that, for each element in the degree, if it's equal to 1, we add 1 to count, which means that, so if k is equal to 1, so for each degree, if k is equal to 1, then we add 1 to count, meaning that this node's degree is 1, so we add 1 to count. This node's degree is 1, so equal to count. So count ends up becoming k, so k is basically count. They're equivalent. And so we do n minus count minus 1 because we take the total amount of nodes, subtract the nodes on the outside, and subtract the central node, and then we essentially get x. Then we take count and divide it by x, and then we end up getting y. So that's essentially the code, and yeah, hopefully this all makes sense. If you guys have any questions about anything, feel free to ask me in the comments. I'll be happy to answer any questions, and yeah, hopefully this helped you.